How do light and matter interact? There are four main ways that light and matter interact. We'll look at each one in turn. First is transmission. Transparent objects transmit light. An example of this would be visible light going through a window. Opaque objects block or absorb light. An example of this would be a visible light not going through a wall. Now, just because an object transmits visible light doesn't mean it transmits other types of light. An example of this would be infrared light. Infrared light does not go through windows or walls, but visible light can go through windows. We see this by allowing light going through a window so that we can see in our rooms during the daytime, but the high temperatures, the heat, is primarily being stuck outside. You don't want that to transmit inside. Other ways light and matter interact are through reflection or scattering, and we'll take a look at this a little bit more in the next slide or two. Reflection, just like reflecting off a mirror, and scattering is a form of this. The final two ways that light and matter can interact are through emission and absorption. We'll take a look at these at a later video. Reflection is exactly what it sounds. Light reflects off a mirror, which has a nice smooth surface. If it comes in at a particular angle, it'll leave and reflect off that mirror at the same angle. This is why it depends on where you're standing if you want to be able to see yourself in a mirror. Scattering, on the other hand, is reflection but off of many surfaces, a rough surface, not a smooth surface. An example of this is a movie theater screen or any sort of projection screen. If you go up and take a look, they're actually a little rough on their surface. This allows the light that hits the screen to scatter and reflect in many different directions, so that people throughout the theater can see what the movie is all about. This happens off of most surfaces, which allows us to see the things around us. If light would only bounce off like it does a mirror off your bed, you might not be able to see the bed, depending on where you're standing, or the walls, or your dresser, or your kitchen. The fact that most objects have rough surfaces allows light to scatter off of all of the different parts of that surface so that you can see the object. Now, light also interacts not just by reflecting, but again, also absorbing. We see objects being different colors because of which colors of light they reflect or absorb. Some objects, like the light bulb in the lamp or the sun, emit their own light. This is similar to the blackbody radiation. Because of the temperature of the objects, they emit light at a variety of wavelengths in a continuous spectrum, which you'll see a little bit more about later. But the idea is that white light is constituted by light of many different colors, the entirety of the rainbow. Our eyes see all of those colors collectively as white. Our eyes see black as the absence of light or color. But if we wanted to see this person's blue vest, we're seeing it as being blue because it's only reflecting blue light and absorbing the other colors of light. So matter can absorb and reflect light even down at the wavelength level. So we see that chair as being red because it's reflecting the red light and absorbing all of the other colors of light. An example of this is going out and looking at cars on a hot summer day. Cars that are dark, such as a black car, if black is the absence of light, would be absorbing most, but not all, we can still see the cars there, most of the light that hits it. Now, light is energy, so that energy has to go somewhere. And we can see that light, or we can feel that energy, by how hot the black car is. In comparison, a white car should be reflecting all colors of light, or almost all of them. And so it would be absorbing less energy. If you put your hand on a white car, it would not feel as hot on a hot summer day as a black car, because the white car is reflecting more of its light, whereas the black car is absorbing most of the light that hits it. Now, light can also tell us the temperatures of planets and stars. Stars create their own light from the internal energy that they hold. Planets can do this as well, but not necessarily at light that our eyes can see. We'll look at this a little bit more in the future. Thermal radiation is the radiation or energy that an object emits based on its temperature. So an object's thermal radiation only depends on its temperature. This is true for all large or dense objects, including stars, planets, and you. So before we go into this in a little bit more depth, we need to talk about temperature and temperature scales. In the US, we primarily use the Fahrenheit temperature scale. In this temperature scale, water freezes at 32 degrees Fahrenheit, and water boils at 212 degrees Fahrenheit. The rest of the world, however, uses the Celsius system. In the Celsius system, water freezes at 0 degrees Celsius, and water boils at 100 degrees Celsius. Both the Celsius and Fahrenheit systems allow for negative temperatures. Absolute zero is essentially the lowest temperature anything could ever be. And we can see how it differs for both the Celsius and Fahrenheit system, although both do include negative temperatures. The Kelvin system is the temperature scale that scientists use, and this is precisely because it doesn't allow for negative temperatures. Absolute zero, the lowest temperature any object could ever be, is exactly zero in the Kelvin system. Water freezes at 273 degrees Kelvin, and water boils at 373 degrees. You might notice that the Kelvin system is exactly the Celsius system with 273 degrees added to it. So any temperature in Kelvin will be exactly 273 degrees higher than that same temperature in Celsius. Now, to understand how temperature relates to this energy, we need to talk a little bit about thermal energy. Thermal energy is a type of kinetic energy. Kinetic energy is the energy of motion. In order to have kinetic energy, an object needs to be moving. And the higher the kinetic energy, the faster the object is moving. Other types of energy include potential energy. Potential energy is energy that's stored in an object. An example of this could be gasoline. Gasoline stores energy in its chemical bonds, and our car's engines transform that stored potential energy into kinetic energy when our cars move. The collective kinetic energy of many particles, for example, all the energy of motion of water molecules in a bucket of water, or in air molecules in your room. If you add up the kinetic energy of all of those particles, that would be the thermal energy associated with the air in your room. Thermal energy is related to temperature, but it is not the same. Temperature is the average kinetic energy of the many particles in a substance. So, for example, temperature is the average kinetic energy of the air molecules in your room. Just like if you look at cars on the highway, the cars on average are going one speed, but there'll be some cars moving faster and some cars moving slower. If we add up the energy associated with each of those cars, we would have the thermal energy corresponding to the cars on the highway. But if we take a look at the energy of cars going the average speed, that would correspond to the temperature related to the cars on the highway, which is a weird thing to think about. But that's basically what we're talking about. We just usually talk about it in terms of molecules. So in the two examples I have here, we can see a bunch of air molecules moving around a room. The lower temperature one all shows everything moving at a slower speed than in the higher temperature one. But in reality, both of these rooms would have some moving at low speeds and some molecules moving at high speeds. But on average, the box labeled higher temperature would include molecules that were moving faster than the box labeled lower temperature. A great example of this is how we cook. If we take a look at this pot of water, its temperature is labeled as 212 degrees Fahrenheit. That's the temperature at which water boils. The air molecules inside of this oven are marked as having a temperature of 400 degrees Fahrenheit. So again, the 400 degrees corresponds to the average kinetic energy, or the average speed of the molecules in that oven. And the smaller arrows inside the pot of water correspond to a lower speed, which is marked by the lower temperature, on average, of the water molecules in that pot of water. So the oven has the higher temperature because it corresponds to average speed, but thermal energy is a measure of the total kinetic energy of all the particles in the substance. It depends not only on the average speed of the objects, but also how many particles are in that substance. So we can see there are far more particles inside of my pot of boiling water than there are inside of my oven. Which would you rather stick your hand inside? The pot of boiling water or the air inside of the oven? That is the difference between thermal energy and temperature.